So you see that? Is that up there?
Perfect.
Yes, it is.
Okay. So we're going to talk about cooling, chiller and cooling. Smaller facilities may not have chillers. Obviously, a lot of your facilities will have chillers. And again, we're talking about optimization and different opportunities. Optimization usually, not usually, always not, disregard replacing chillers. So this will be more about optimization. Smaller systems, yeah, you can look at replacing. So again, this is those are called primary systems. They serve those secondary systems that we just discussed, the ventilation system. They do have a significant impact on comfort, especially if they cannot meet the load, if they cannot provide dehumidification, for example. Chiller are particularly complex equipment, if you ask me. When I do recommissioning, I mean, I'm not an expert in chillers. That's why I'm so glad people from Trane are here. When I deal with chiller, I usually have some of my colleagues to assist because they are a more finicky machine than, let's say, and I don't want to demean boilers, but I find them more difficult to, they have their personality, if I can say. You have two identical chiller and they just don't sometimes behave the same for some reason. So there is obviously opportunities both in terms of energy usage, better interior condition. If you can, provide more capacity, sometimes with the same machine, and we'll talk about Delta T, for example, that can create limited capacity on a given machine. And it also has, it's very often one of the highest demand equipment in the building. We're talking about Class A and Class B. If you're a Class A and for some reason you start your chiller, a second chiller or a third chiller at a wrong time of the day, that can really hit you bad on your GA cost. So if there's one equipment that can actually hurt you on GA, it's a chiller. It can hurt you on demand if you don't start it properly, if you really load it up and fully load for an hour or a half hour. So those are things you have to be aware of. Ways to save through optimization. Again, you need to know your CFR. What will be your cooling set point? Are you going to try to keep 21 degrees like we see sometimes in retail, or 20 degrees in retail and office buildings, which are really, really low set point? What is the dehumidification that you want to achieve if you use dehumidification? Those are all things that need to be specified so you know what temperature chilled water you will need, what kind of reset you can use, when you can reset. If you've got multiple chiller, which is very, very likely, depending on the type of chiller, how are you going to sequence those chillers? How are they arranged? You just don't need to know I have 3 chillers. Are they 3 chillers in parallel? Are they 3 chillers in series? Are they in series counterflow, like the most efficient type of combination sometimes in larger plants? So you need to know that before you start optimizing. And the type of chiller. Is it inlet guide vanes, or is it VFDs or VSDs? The VFDs chillers are actually more efficient at part load, so you will sequence them differently than if you have inlet guide vane chillers, or if you have a magnetic bearing chiller. They're way better at part load, so you would tend to run them more often in parallel than in sequence, in lead lag, for example. So those are all things that when you have a central chilled water plant, you need to know properly. And when I do an audit, well, I shouldn't say surprised, but very often I'll ask the operator, what kind of chiller plant do you have? And more often than not, I don't get the proper description when I do the interview. Then you go on site and you realize, well, this is not what I was told. And obviously, I don't blame the operator, especially when they're fairly new. It's a question of training. And how do you want them to properly run? Sometimes they actually have no idea how it's run. It's all done by the control company. They have nothing to do with it. Or sometimes they fiddle with it too much. So it goes both ways. So training is, again, something very important when you start talking about the chiller. You obviously, when you have a chiller plant, you want to take advantage of free cooling. I talked about that in the previous section. When you talk about free cooling, you've got two main type of free cooling: the air side free cooling with your economizer on your air handling unit, and you get your water side free cooling where you use a plate heat exchanger typically with your cooling tower. Depending on the type of chiller plant you have and the type of humidification you have, you may go from free cooling on using air side to free cooling using the water side. If you've got a heat recovery chiller, well, free cooling will rob you from heat recovery capability. So you sometimes, well not sometimes, most of the time, if you have a heat recovery chiller and it's worth running a heat recovery chiller, and I insist, is it worth running the heat recovery chiller, then you don't want to unload that chiller. You want to keep it loaded so that you can recover that internal heat, that generated heat from inside your building, to heat the perimeter of the building and to heat the fresh air coming into the building using that recovered heat. And the reason I said when it's worth it, a heat recovery chiller is less efficient than when a chiller runs as a cooling chiller. So because your condensing temperature is going to go higher, your COP or your kilowatt per ton will not be as good. Therefore, you will pay. Electricity in Ontario is about 7 times more expensive on average than gas. So it's sometimes not worth running a heat recovery chiller when your electricity is cheap and your electricity is expensive and your gas is cheap. But be very careful when you do that kind of analytics. Always wonder, does my heat recovery chiller impact my demand? Does it impact my global adjustment, for example? If it does not, and you're a Class A, then you know what? Your electricity is actually cheap. And Stephen, would you agree with that? The kWh, if your heat recovery chiller does not impact your demand, is actually not very expensive. No?
Yes, agreed.
Okay. I was just wanted to make sure, asking, so things to keep in mind when you have a heat recovery. For example, in Quebec, and there's people I know online that are from Quebec, heat recovery chillers are very common in hospitals because it's actually economical to run it, because gas is more expensive than it is in Ontario, and electricity is actually cheaper. And with the COP of the heat recovery chiller, you'll see that in many hospitals. And obviously, because electricity has a lower greenhouse gas emission factor, you actually save greenhouse gases by going with your heat recovery chiller. Obviously, you also have to look at the type of condenser you have, or heat rejection. Most chiller plants use open towers, so water cooling towers, but you can sometimes have a dry cooler or adiabatic cooler, which has like kind of evaporative cooler. And the way you run those is always something we'll look at. I know I'm out of order here somewhere in the slide, but I'll tell you that right now. If you have cooling towers that have VFDs and you run your cooling tower in lead lag manner, go right back when you're back, change that right away. They have to be run in parallel. Cooling towers, obviously, that are common to multiple chillers, not if they are dedicated to a chiller each, but cooling towers with VFDs should always be ran with parallel operation as much as their capacity turn down allows, obviously. But that's one thing that we systematically change. We see that less and less, but sometimes people install drives, forget to change the control sequence, and the fans on the cooling tower keep running lead lag even though they have VFD. So make sure that is not the case in any of your facilities.
Michel, I just want to reinforce something you said earlier, or maybe just qualify it. You talked about the GHGs and the heat recovery chiller, right? And in Ontario, you got a low carbon mix in the electricity. But if you're in a jurisdiction where there's a high carbon mix in the electricity, then you've got to always look at, you've got to look at within your jurisdiction the relative prices, the price of demand, and then the carbon impact as well. So don't assume that every jurisdiction is going to give you the same optimal result. And it depends on what your goals are. If your goal is cost only, your goal is carbon or carbon and cost, then you've got to factor all those in to that business case.
Yeah, that's an excellent point. Thank you, Steve, because you're right. The GHG emission factor for different provinces varies very, very widely. So you have to look at the cost. So it's not like a lot of the heat recovery chillers have been taken out of service in Ontario, for example. But I think they will be coming back in eventually because electricity is pretty clean in Ontario. And if you do your proper analytics and you're a Class A, very likely that it's not that bad to run those heat recovery chiller because your kWh cost may be just a few cents, like 5-6 cents, and never ever use the blended rate in your energy savings calculation. This is not part of the slide, but any energy savings calculation, if you take your yearly cost for electricity and your yearly total kilowatt hour and you get a blended rate, this is just good for reporting. Never use that in any savings calculation because you will fool yourself in thinking you have good payback.
Yeah, I can tell you right now, I can guarantee you that the blended rate will get you the wrong answer.
Yeah, so I know that's not part of the slide, so I'll keep moving, but this is so important. Never use a blended rate for electricity in your savings calculation. And if you do, if you are a Class A customer and you really want to save, you could use thermal storage. So obviously, thermal storage is not a cheap solution, but if you have already the storage and it's not used, I've seen places where that was the case, or if you can use storage, you can actually drop significantly your demand during the 5 peak hours. Actually, you'll probably use it more than the 5 peak hours because you don't want to miss one of those hours, so you'll use it more often, but that's definitely something you'll do. The question I'm often asked, does thermal storage save energy? For heating purposes, it does not. If you put thermal storage for heating purposes, which we do in Quebec, it costs you kWh because there's losses from the storage. In cooling, it may save you because it can allow your chiller to run at a better efficiency, and also you can run them off peak. So it can actually save you both energy, but most likely cost, not only because you avoid the GA, you can avoid GA hours, but you can also, if you're on the hourly Ontario energy price, you can run at times where electricity is cheaper and then empty your storage during the high cost of the daytime hours. And like I said, so I talked about that already, and I'm checking my time here. I've got a few minutes left. Make sure you know what type of chiller you have, what type of loop configuration. And I know I don't want to go too much into technical details, but again, things you need to be aware of. There are systems that are called primary only. That means the water goes through your chiller and then goes through the building with one set of pumps. So if you want to go variable flow, you can, but you have to know what are the limits, the constraints of your chillers. Chillers, like I said, can be finicky machines. They're designed to have a flow of 2.4 gallons per minute per ton of capacity. Most of them, you can take them down to about 1.2 gallons per minute in theory. They don't always work properly when you do that. If you have more modern chiller, you can actually use what we call variable flow primary only. Most of the older systems are primary, secondary, and your secondary loop has a set of pumps which you can put as variable speed, and your primary pumps with sort of the chiller can remain constant speed, so your chiller are, humming away happily without flow variation. So that's something you need to know. It will affect the measure. If you're in luck, you have a secondary loop with a central bypass. And actually, you're in luck in the sense this is not a very efficient system in the sense that you're bypassing centrally when your load is low. But the good news is this can be converted at a fairly low cost to variable flow because you don't have to change a bunch of three-way valves that would be at every of your coils. you can only change the setting on the bypass, close that bypass, install a VFD, and convert the system to variable flow. There can be sometimes more complexities. I'm simplifying here, but that is a measure that I've seen implemented, and I have implemented in a number of buildings. We talked about very slightly about heat recovery chillers. You have two types of configuration. There's this, I'm making it simple here. You've got what we call the double bundle chiller. It's called the one at the top here is the double bundle chiller. The reason it's called double bundle is because it's got two condenser bundle, one for regular operation and one that's used for heat recovery operation. Not all manufacturers now make double bundle chillers. So what you can do is have a regular chiller, but an external heat exchanger that will provide you with your heat recovery. A double bundle chiller typically will be able to achieve higher condensing temperature. So your heating loop is still a low temperature loop. That's the one thing you have to know about heat recovery chiller. They usually work with a low temperature loop, not a high temperature loop. If you have a high temperature loop and somehow you still want to do heat recovery, you would have to have like a heat pump to boost that temperature up. That's not very common. Usually it's on the low temperature loop. Ideally, if you try to send that water to, let's say, radiation heater, but also to makeup air units or to air handling coils, which are low temperature coils. Those can actually heat because they usually do air preheating, or they are tempering the air to about 70 degrees or so Fahrenheit. So those are good loads to send the heat recovery heat in. Reheat loops are also very often used in the heat recovery chiller because they are low temperature loops. So, and those heat recovery chillers are basically they're heat pumps. In the winter time, they take the internal heat and send it to the perimeter. So it's basically a central heat pump that you use in the winter.
I just have a quick question. Can you just put a little bit of light on the cogeneration? So we have a cogeneration here at the Hamilton General Hospital, and do you think it's a good idea to actually use the heat recovery chillers when we have a cogeneration, because we are generating our own electricity and we have a low temp and a high temp, but at the same time we have cooling towers that's just being dedicated for the just for the chillers. So do you think that it could be a good idea when we use a cogeneration and a heat recovery chiller?
Well, like I said, it's a kind of case by case, but if you have a low temperature loop and you have cogen, I would tend to say yes, that it would be, again, you won't be able to take a high temperature loop system where you have no low temperature and say, I'm going to use a heat recovery chiller. But if you have the stability of recovering the condenser heat, sending it to a loop, yes, I'd say at first glance, it would be a good thing to have. Okay. And I can invite, hey, Jeff, what's your colleague's name that's in Ottawa?
David. Hey, it's Matt. I'm in the GTA, but I think I could take this question. So I would encourage you to use your heat reclaim chiller to satisfy your low temp heating requirements, like your reheat and preheating domestic water and some of your air handlers, and then use your cogen to satisfy your high temp heating requirements, like the building radiation, the steam for medical processing, all your autoclaves, all that. So if you can, because a cogen will make higher grade heat than a chiller will. So knock the low grade heating off with the chiller. Use the CHP for the high grade heating requirements.
Yeah, I would tend to agree with that, Matt. And there's actually a methodical way to answer that question, and it's called pinch analysis. It's used in the industry.
Exactly.
You can actually do this and show where the crossover points were. So I can send some information out on that. I mean, it's a pretty complex approach, but somebody who's good at it could actually give you an operating strategy based upon that and all your different temperatures. But it comes back to what Matt said. You got to match your temperatures, right? And don't degrade a high temperature to low temperature and so on, right? You've got to find the optimal combinations.
And I'll just add, if you've got your CHP rejecting heat in the middle of the summer and you've got a heat reclaim chiller running, maybe you want to think about running one of your more efficient conventional centrifugals. Use your heat rejected from the CHP to take care of your reheat, your low temp heating. Shut that heat reclaim chiller off or unload it. But then the flip side of that is in the middle of the winter, when you need a lot of heating, run that heat reclaim chiller, let it do as much as it can on the heat recovery side, and then use the CHP for the medium and high grade heat. Just kind of maybe opposite to maybe what you were thinking.
Well, that's pretty much what I was thinking. You need a low temperature loop, and you reject low temperature.
Yeah.
For their heat recovery, absolutely. That's my was too.
Yeah.
Okay, so thanks, Matt. So I'm gonna have 5 more minutes, and then I'll pass it on to guys at Trane. Things that need to be reviewed when you have your chiller system. Look at the delta T, for example, on your loop. If you've got, let's say on the secondary loop here, if you've got a 2 or 3 degrees Celsius, or sometimes it's even 2 or 3 degrees Fahrenheit delta T, you may have an issue of over pumping. You can do a pump test. That's a test we do often in recommissioning to establish what is the actual flow in there. And you may be able to adjust. You can actually adjust with a VFD, even if it's not built as a variable flow, a bit like we said before for the ventilation system. We get some more complexity, but it's possible to put a drive on there and set it at a constant speed, but instead of using a throttling valve, you just use a VFD to adjust the flow to a more adequate value. I've been in buildings, not necessarily hospitals, where the cooling towers, you also check the delta T on your cooling towers, where the delta T was so very low and the pump used to be throttled. And somebody saw the throttling and said, hey, that's bad, it's throttled. So they opened it up. Because they thought throttling is inefficient. Well, throttling is inefficient compared to VFD, but opening up a throttle valve is really, really inefficient. So always be on the lookout for your delta T's. If they're very low, depending on the load, obviously, it is a sign that it may be over pumping. You may have other issues. There's like 10 different possibilities when you have a load, and I say 10. There's a large number of possibilities. Could be dirty coil, could be, like I said, a number of things, but look at the flow. That's an easy one to look at. Also check, is the loop flow, can it be varied? Can I go variable flow? The type of reset, are you always keeping the same supply, the same set point for your cooling tower? Is your cooling tower set point realistic? Some people put 19 degrees. I want 19 Celsius as my return. They know it's never going to be achieved most of the time in the summer. So they also have VFDs on those fans. So the fans never catch up. So there's something called wet bulb reset for a cooling tower. So look at different reset strategies, but look at the total impact of your reset strategy. If, for example, you decide to reset your chilled water, you're supplying, let's say and I'm sorry, I go from Celsius to Fahrenheit, you're supplying at 44 Fahrenheit chilled water, and you decide to reset that, you say, hey, if I increase my supply temperature as it gets colder outside, I will save. So you increase that supply from 44 to, let's say you're aggressive, 54. Well, now you're sending 54 degrees in your air handling coils, cooling coils, but it's, let's say, muggy outside. It's like 19 degrees, 100% humidity. Well, at 54, your coil has no more dehumidification capability. So you'll have a hospital that has maybe its cooling set point met, but it will be super humid. It will be uncomfortable. You will not meet your CFR. So when you do reset strategies, always look at the global picture. If you've got variable flow and you reset your chilled water, that means you're sending, let's say, warmer water through your system because you reset it. You've got variable flow. So the space temperature or the coil sensor sees that, hey, the water's warmer, I need more flow, I'm going to open the valve. If I open the valve, the pump speeds up. So yeah, you're saving chiller kWh, but you're increasing your pump kWh by doing that reset. So when you do those kind of strategies, always look at the big picture. Otherwise, you may end up in the end paying more, which is possible actually when you do chilled water reset on the variable flow system. And that's why if you look at some of the standards, such as the ASHRAE 90.1, they do not require reset strategies on chilled water when they variable flow because of the impact it may have on pump power. And it doesn't mean not to look at it, but just to be careful when you look at that. You will have also the X system in the smaller system. And some of the measures we discussed previously, such as reducing the airflow to, or cutting the airflow to some zone, may provide problems for those systems. If you have a DX systems with a gas heating coil, and you reduce the flow capacity, well, if that, depending on the number of stages of cooling, you may run into issues. So you may actually need to reopen those dampers when there's a high cooling load for the rest of the system that is not isolated if you have DX. So again, the DX, for those of you who are not familiar with that, that's direct expansion. So those are your standard rooftop units, for example. And they do need a certain airflow both for heating and cooling. And if you start playing around with the with isolation damper, well, you may run into issues with the heating and cooling section. So always be aware of that. For those rooftop units, DX systems, they're often forgotten in terms of maintenance. They're on the roof. You go there and the dampers are not very good. Economizer may not be working. They may not have been centralized for some reason, depending on the OEM control that was on there. So always keep on top of that when we're talking about cooling. Make sure the economizer is working on those and that the set points are properly set, especially when they have not been centralized. The last system before I pass it on, and the only reason I put it in there is because we see it more and more. You should not see that very much in most spaces in the hospital because they're not allowed. But those are VRF systems, variable refrigerant flow. So you will have many what we call heads. So you'll go in here. So those are heads. You'll see that in type 3 spaces sometimes. So those are all heating or cooling units. They're connected to a given outdoor unit, but they can actually be either a heat pump. So all of those units will be either heating or cooling when it's a heat pump model. If it's a heat recovery model, each of those units can be in a different mode. And what you have in those lines is refrigerant going in and circulating all over the building. They are efficient, but they can lose efficiency quickly if they have very long service lines. So if it's very long to get to the outdoor unit, to the indoor unit, the performance drops. And then you also have to think that you'll have refrigerant running all over your building and all of those lines. That's why some places, they really don't like to have VRF installed because of the number of refrigerant lines. They actually had to modify the mechanical code to allow some of those systems because they would have too much refrigerant and the space they were serving would have become mechanical rooms. So they would have to have exhaust and sensors, but the code was modified for that. If you have some of those, again, it is efficient, but the drawback is, a lot of refrigerant. Performance is site dependent. And until recently, controls were a pain because it was really hard to centralize. Like I said, if you have that, it will be likely in the administrative area of the building because they are technically, CSA 317 would not allow that in type 1 and type 2 spaces. So I think it's 3:15, and the schedule says I'll pass that on to Jeff.
Just before we do that, we do have one chat question from Carl. Is there more savings reset temperature on the condenser side, like on the cooling towers, or reset on the evaporator side? Or is this dependent on manufacturer or the type of chillers, for instance, screw versus centrifugal?
Well,
hey, Dave, are you on the line?
yes.
Dave Titus?
Yeah, I'm here.
I don't know if you can open the chat, if you've got the chat open there. It's a good question.
Let's see, where do I see this chat?
Okay, did you want to answer that? It's David, I think.
Yes.
I'll tell you on my end. Technically, you get more savings per degree C of reset on the on a constant flow system when it's on the chilled water side. But it is more problematic usually, and you get a little less savings on the condenser side per degree C or per degree F of delta T. It's about 1% per degree of reset, a degree F of reset on the condenser, and about 2% on the chilled water side.
Right. Yeah, no,
We have one more quick question from Julia. Which CRF code number did Michelle just mention?
Sorry, it was CSA 317. I believe that Julia is probably referring. I did not. So that would be CSA 317. Z 317.2.
0.2, right. Okay. All right. Over to you, Jeff and Dave.
Yeah, Dave, maybe you want to walk us through.
Yes, slides you like to show?
I can share my screen. I have a couple of things here.
Okay,
up on my screen.
Dave wants to share a screen?
Yes.
Yes,
Okay,
please.
I'm going to make you an organizer, Dave. So just hit the third button over which says screen and you're all good to go. Perfect, we can see that. Dave, your mic is muted.
Thank you very much.
There we are.
Perfect. Yeah, so I'm happy to share a nice success story of a fun project that Trane was happy and lucky to be involved with. This goes back to 2014, 2015, when the Trane Ottawa group was working with our friends up at the Timmins and Area District Hospital, or Timmins and District Hospital, and they had a challenge that we were happy to help work with them through. Essentially, they needed to upgrade and replace some of their chilled water infrastructure, specifically their chillers. Where this started essentially was they had 4 existing chillers. They were air-cooled chillers, about 150 tons each. They were 20 plus years old, so they were nearing end of life. The specific challenges that the client had, they actually had the nice problem of having excess capacity. So they really only ever ran 2 out of those 4 chillers, and certainly any hospital will enjoy having redundancy, but that may have, for them specifically, actually been more than they needed and was potentially resulting in additional maintenance costs. They certainly wanted to improve dehumidification and temperature control in some of their critical zones through the hospital. They wanted to, maintain some redundancy, at least a reasonable amount, but within reason, and obviously balancing out operating costs as well. They wanted to take advantage of some very lucrative hydro incentives at the time. That was when there was a utility incentive through Hydro One that was $800 per peak kilowatt of demand reduction, which obviously can go a long way if you can tap into that. So that got everyone very interested. And of course, as any customers, any hospital, or anyone who operates a building can attest to, they wanted to reduce maintenance costs as well as reduce their operating costs specific to this as a result of the energy usage of this system. So the design that that the Trane team with the hospital and the local consultant came up with was really hingent around thermal energy storage or ice storage being added into the system that was there already. So what ended up happening is the 4 chillers that were there before ended up being retrofitted to 2 chillers of a similar size and 8 thermal energy storage tanks or ice tanks. So if I have so this was just a picture coming off the roof of the 8 ice tanks that ended up going in there. The original picture here shows where the chillers were originally. This structural platform still actually remained. There were 4 chillers here before. 1 where this kind of pump station is here, 2 where the new chillers were, and then there was a kind of an empty bay off to the left here where the picture doesn't show. So there were 4 originally, and then after the project was done, there were 2 of similar size, plus this pump station, plus the 8 ice tanks off the roof, mounted on an on-grade slab. So if I can quickly show here. So there were a few things from a design standpoint that we had to consider here. First off, the original system that you can see here was 4 individual air-cooled chillers, each with their own dedicated pump, all operating on chilled water. The hospital was operating on a very typical 44-54 Fahrenheit chilled water system. All of those 4 chillers then pumping into their main chilled water supply in return that goes to their various cooling loads and air handlers throughout the hospital. So whenever you introduce ice storage, obviously glycol needs to be introduced into the system. These ice storage tanks work on the principle of using your chiller to make sub-freezing glycol at night or whenever needed, depending on your strategy, to freeze the tanks. Within the tanks, there is a skeletal network of plastic tubing with water on the outside. So the tubes, the tanks are full of water with these tubes inside them that the glycol runs through. So you run sub-freezing glycol through the tubes. That freezes the water on the outside of the tubes until you essentially have a solid block of ice. And then during the day or whenever, again, your strategy is to use that cooling, that stored cooling capacity, you then pump glycol through that system and you slowly melt the ice on the outside of the tubes, which of course cools your chilled water. So these 8 tanks here are essentially equivalent to about 150 to 200 ton chiller, depending again how quickly you want to melt the ice. Just like an electric battery that would be measured in kilowatt hours, a thermal battery like this is measured in ton hours. So 1 tank may be 150 ton hours, so 8 tanks may be 1,200 ton hours. So you can, if you melt that over an 8-hour span, you essentially have a 150 ton chiller for 8 hours. And then of course there is some flexibility and resiliency in the system for how that can be operated. So this kind of design concept was chosen for a few reasons. One, it maintained at least the 300 or so tons of capacity for the hospital, which we realized after a load profile analysis really dropped off to about half of that at night, even on a warm Sudbury summer day. So that's why we have 1 chiller, which up here, which remained on the existing water loop, which could provide cooling at any given time. And the second chiller, which was put into a glycol loop. You can see the chiller here, the ice pumping module and the tanks are all on glycol, all connected through a new heat exchanger inside the building, then connecting, then having water on the other side tied into their existing system. So this chiller, as part of the ice system here, can either create sub-freezing glycol to freeze the tanks at night, or it can work in conjunction with the tanks to provide cooling to the hospital during the day. And that strategy for when you use that really comes into play, or really hinges on the strategy that you're trying to use. In this case, we were trying to reduce the operating cost by load shifting and using less kilowatt hours during peak hydro rate times. So these tanks are essentially frozen overnight when kilowatt hour or dollar per kilowatt hour rates are very low. And then during the day from about noon to 7 o'clock, which is when the hospital there sees their higher utility rates, that's when we turn a chiller off and use as much ice as possible for those 6 or 7 hours, using, you know, one chiller at part load to top up any additional capacity that's needed. And in doing so, significantly reducing the monthly and annual kilowatt hour cost that the hospital sees on their utility bill. In addition to this, just some other design modifications that were made. I'd mentioned the system was originally on a 4454 chilled water system, and for a couple of reasons, this system was actually modified to work on closer to a 4054 chilled water design. The lower temperature of chilled water being flown through the hospital with the existing air handlers and existing cooling coils that were there allowed that existing infrastructure to provide better dehumidification from those units, and also really helps with, you know, anytime a building is running at partial load, you can often get low delta T syndrome, where you get you know, regardless of what you design your system for, you don't get a very wide delta T coming back, which is obviously detrimental to your pumping energy. So if we can provide colder chilled water, get a better return temperature, we're both improving temperature and humidity while minimizing the pumping energy required for that system. So let's see, so I'm throwing up another slide picture here. So this is a picture of just the BAS interface operator screen that we provided on this project. Controls optimization was certainly a big piece of this as well. This shows a nice visual schematic of what the system looks like in terms of having your chiller and your ice tank and your pump on the glycol side with your heat exchanger. So this you can essentially treat as one big chiller in parallel with your water chiller, providing your cooling to the building. And as part of the controls, we are monitoring the discharge air temperature from the air handlers for all of the critical zones that the hospital is concerned about over here on the top right corner. And we can do critical discharge temperature reset based on any of these. So if, for example, your OR temperature air handler leaving temperature is creeping up, we may do a system reset on the whole system to make slightly colder chilled water to make sure that we are maintaining required temperature and humidities in some of those critical spaces. So kind of all over the map here, but this is the general idea of what we did for this project. The big takeaways here, one obviously was a very large hydro incentive. I believe it was definitely six figures. I think it was somewhere close to $200,000, which, as the presenter, I think Michelle or the presenter mentioned before, ice storage can certainly be a bit of a price premium when you talk about adding the cost of tanks and other components to the system. There are certain applications where it can be closer to cost neutral, but certainly it is a premium system, and usually a price tag is associated with that. But when a hydro incentive exists that pays that rewards demand reduction, that is really well suited to ice storage, and those incentives in this case can really pay for the premium that the ice storage component would have cost. So rather than replacing like for like chillers, they paid more for the ice storage, and the incentive really paid for that increase in price to get that better system. The hospital is certainly seeing lower electricity bills by using as much off-peak, or by shifting as many off-peak kilowatts as possible, and minimizing the on-peak kilowatts. They're definitely saving anywhere in the, I'd say, 30 to 40% of the utility costs specific to this system. Of course, not for the whole hospital, but specific to the usage of this chilled water system. And also, we've minimized the amount of equipment involved. They had 4 chillers before that were all operating on water in Timmins or anywhere. For us on the call here, we'll need to drain down and winterize those chillers. So rather than having to winterize and fill 4 chillers each year, now they're just doing it to 1 chiller, and the 1 glycol chiller can essentially stay charged all year with 50% glycol in there, which is well protected for the Sudbury winters. And of course, rather than having a service maintenance agreement on 4 chillers, they're only looking at 2. And the ice storage tanks really require next to no maintenance. They sit there quite happily with a lifespan of 20+ years with next to no maintenance other than a little bit of water treatment. So the hospital is certainly benefiting from reduced maintenance costs and headaches as well. So this has been in place now for, yeah, go ahead.
Sorry, Dave. Healthcare Energy Leaders Ontario was involved in that project, and I thought it was a great project right from the get-go. We do have a question from Devin Clark in the Sioux area. He says, great project. Was it fully automated to switch plant modes to reduce human error?
Yeah, so great question. And certainly there are options for the level of automation that a system like this could have, depending on the comfort or the interest in how hands-on the specific operations team at that hospital wants to be. This one is set up to be pretty well automated based on that kind of noon to 7 p.m. Hydro rate or hydro schedule that I was mentioning. So this one, we essentially burn as much ice as we can through that period, knowing that the utility rate is pretty well fixed for the specific customer. You know, for a customer that may be a Class A customer or may have a special hydro rate or fluctuating hydro rates, of course, that control strategy would have to be modified for that specific customer. But this one is definitely kind of programmed to just kind of hit the easy button and let it do a similar thing throughout most days, which is, again, going back to discussing with the customer what they wanted and what is going to ultimately get the results that we're looking for.
Yeah, for sure. Sounds good.
Yeah, so that's really all that I have without taking up too much time, because I think we're getting to the end of our day here. But certainly, if any other questions come up, I'd be happy to address them.
Yeah, no, great presentation. Good way to finish off the day. Does anybody have any more questions, or Stephen, do you have?
No, I think we're good from my point of view. We'll probably follow up with obviously the materials and also maybe some of the reference links and things like that for folks too.
Yes. Yeah. Michelle, anything to add, or good?
No, that's all good. Thank you. Was quite interesting. Thank you for the case study.
Yeah, I will be sending along. I found a reference to using that pinch analysis technique for managing a hospital, basically heat network and cool network. So with CHP in it, so it gives you the ability to find the optimal conditions. So great question.
Yeah. Yeah, there was some enthusiasm about that on the chat, so please do that. Anyways, thanks everybody for great day one, and thank you, Stephen. Thank you, Michelle, for your time today. And just a reminder, next session is on October the 6th and beginning at 10:30. So if you could sign on by, say, 10:15, that would be great. And then our last session will be on October the 8th, 2 days after that, and again beginning at 10:30. So thanks everyone, and enjoy the rest of the day, and stay safe.
Yep.
Thanks,
Take care.
everybody.
Great job. Thank you.
Good afternoon.
Take care. Thanks, Dave.
Thanks.